Hello and good morning, good afternoon, or good evening, depending on where you are in the world, where you're joining us from. My name is Jason Senga. On behalf of TA Instruments, I'd like you to welcome you and thank you for joining us for this exciting new product applications webinar. Today's speaker is Dr. Gray Slough. Gray is currently a product specialist in the thermal product group at TA Instruments. Dr. Slough received his BS in physics from the University of Texas at Austin, 1983, his PhD in condensed matter physics from the University of Virginia in 1990. He joined TA Instruments back in 1998 as an applications scientist, and currently within the thermal product group, he works to help define and develop the thermal analysis product lines at TA, provide technical support to both internal and external customers. The title of Gray's webinar today is Measuring the Influence of Humidity on Material Properties. During this webinar, there is a section on your screen and your interface that you should be able to submit questions. I will either address the questions within the chat, or the good questions I'll save and we'll answer those at the end of the session. Answer as many as we can. And so there are also some areas there that would include some resources, such as brochures for the products that we'll be discussing today. So we have a couple new products that we are excited to discuss, applications that go along with it. So with that, I'm going to hand it off to Gray. Gray, the stage is yours.
Thanks very much, Jason. So I'll add my welcome also to everyone who's attending today. And as Jason said, the title of the talk today is Measuring the Influence of Humidity on Material Properties. For now, I'm just going to go ahead and turn my camera off, and then we'll just go right into it. So if you're familiar with thermal analysis, you're familiar, I think, with most of the control parameters that are used to set up experiments. Now, obviously, thermal analysis, temperature is your main control parameter. Most thermal analysis experiments are done by scanning at some linear rate, or potentially holding isothermal at some temperature, in which case then time becomes a control parameter for you too. So that fairly well describes two main control parameters for something like a differential scanning calorimeter or a thermogravimetric analyzer. When you start talking about thermomechanical analyzers, then force also becomes another control parameter that you can use to set up experiments. It's becoming more popular these days that customers want to add a fourth control parameter, and that fourth control parameter is relative humidity. So why do people want to add relative humidity as a control parameter? Well, of course, water is ubiquitous. It's everywhere. And, it gets on the surfaces of all materials, and it can actually be absorbed into the interior of a number of materials. So it's going to affect the properties potentially of anything that you're going to make. And in that sense, then you have to be aware of effects upon processing, storage, packaging of your materials, and you have to engineer them and tailor them for realistic RH conditions, the RH conditions that you think these materials potentially could be exposed to. At the bottom of this slide, I have a couple of quotes that I found in some papers that I've read here. First one is related to the electronics industry. So moisture-induced failure is one of the major reliability concerns in electronic packaging. And then the second quote here is related to the pharmaceutical industry. It says, in pharmaceutical manufacture, the need to control humidity may not be just to ensure stability of the API and prevent any degradation due to hydrolysis, for example, but also to ensure that quality drug products with respect to other critical quality attributes are produced. So understanding the impact of humidity on materials is a very important thing. So with that, then, big part of this webinar is to talk about and introduce two new thermal analysis instruments that TA is proud to offer to its customers, which offer relative humidity as a control parameter. So the very first instrument here is the Discovery SA. This is a dynamic vapor sorption analyzer. It's actually the replacement for our very successful Q5000 SA. So this is an instrument, at its heart, it's a thermogravimetric analyzer, so it is measuring weight changes as a function of temperature, but in this case also, most importantly, as a function of humidity. So the things that you can learn from an instrument like this include hygroscopicity, which is the ability of a material to take up water and potentially release that water, hydrate formation in pharmaceuticals, humidity-induced phase transitions, wetting and drying. We'll talk about a lot of these applications as we get into the talk. And as far as the industries that have interest in this type of instrument, certainly pharmaceuticals, polymers, foods, and electronics are right at the top of the list. But then inorganic materials, absorbents, catalysts, and building materials, those types of industries will also find use in an instrument that operates like this. So some of the unique features of this instrument include an auto sampler, which the base auto sampler is a 10-position auto sampler. There's also an option to have a 25-position auto sampler. That particular auto sampler comes with a pan punch, so that samples that are sensitive to moisture or to maybe oxygen in the atmosphere, they can be sealed and then punched prior to putting into the instrument. There's also an autofill pump for this particular instrument, which will refill the saturator during runs so that you have extended run time on the instrument. As we'll see, a lot of experiments that are done with humidity are actually very long experiments. Other key features include the true mass microbalance. We'll have a slide or two talking about the performance of the balance. True 0% RH, we've improved the drying capability of this instrument over the previous generation. It has a wide RH and temperature control, so the temperature range from 5 to 85 C with RH control up to 98%. Actually, a plot of RH versus temperature would be a rectangle in that case. And this is 21 CFR 11 compliant, which is very important in the pharmaceutical industry. In the lower right-hand corner is just a chart of some of the specifications for the instrument. We've already talked about the RH control range and the temperature control range. So there are a few others there. There's two weight ranges for this instrument, a 100 milligram and a 1 gram weight range. The second instrument that we'd like to talk about, this is a brand new instrument now. It's the Discovery TMA 450 RH. This is a dedicated, just as the SA is a dedicated instrument for measuring weight changes versus relative humidity, this is a dedicated instrument that is dedicated to measuring dimension change. So it functions at its heart just like a thermomechanical analyzer, but it is dedicated to looking at changes in dimension with respect to temperature and, most importantly, relative humidity. So what can you learn from an instrument like this? So you can measure something like coefficient of hygroscopic expansion. Folks who've worked with TMA in the past know that there's a physical property called coefficient of thermal expansion, which measures the dimension change of material and normalizes it with respect to length and temperature. And it's a physical property that many people find that they need to know if they're going to make multi-layered materials, to find compatibility between different materials. Coefficient of hygroscopic expansion is very similar in this case. We're looking at dimension change normalized with respect to material size and percent RH. Again, we can look at hygroscopicity, which again would be the ability of a material to take up water and release it. Shrink forces, changes in glass transition temperature as you load, material absorbs water. In this case, the industries that will find large use from this Electronics, polymers, and building materials are the ones that immediately come to mind. But of course, pharmaceutical, inorganic materials, absorbents, and catalysts are also industries that should find uses for this type of instrument. Some of the unique features for this particular instrument, and an image of it again is shown in the upper right corner there with the humidifier accessory attached to it. We have the broadest range. This instrument has the broadest range of relative humidity and temperature of any other instrument on the market that does similar types of measurements. The humidity accessory, again, the box that's shown connected to the instrument through the transfer line, also allows for manual filling, so it has a reservoir, just as we spoke about with the Discovery SA, which allows for manual filling, again, for extended experiments. Experiments here are also very long, just like they are with the Discovery SA. Some of the key features here, we have the widest range of low expansion quartz fixtures. In fact, every fixture that is on our Discovery TMA 450 model, except for the volumetric probe, is available on this particular instrument as well. We have advanced modes here, so we can do modulated force, which allows you to do dynamic experiments. You can measure creep, stress relaxation, or isostrain experiments. And this instrument is also 21 CFR 11 compliant. And again, there is a chart of some of the specifications. You can see here the humidity range is 5 to 95%, very similar to what it is on the Discovery SA, and the temperature range is 5 to 120. So we have a little bit higher top end on this. I will show a chart of the temperature versus a relative humidity range here a little bit later. It's not the rectangle that it is on the SA, but we'll see what a chart of that looks like. And then some of the other specifications there, such as maximum sample size, sensitivity, those are exactly the same as they are in the Discovery TMA. So one thing I want to point out before we actually start looking at some data here is that RH experiments are typically very different from regular thermal analysis experiments. So I mentioned in the very beginning that typical thermal analysis experiment is done with, most experiments are done by scanning temperature in some linear fashion, 5 degrees a minute, 10 degrees a minute. That's not the way that typical experiments are done when controlling RH. The reason is that if a sample is going to absorb water, it's going to take some time to do that. So more than likely, most experiments are done by stepping humidity. And so you can see in the upper graph, you will step the relative humidity, and then you will plot and monitor the change in your parameter. In this case, either weight or dimension change over time, and it will slowly change and reach some level of stability. And in that case, you then move on to the next change in relative humidity. And our software allows for, once a particular set of stability criteria are met, so that the instrument can automatically move on to the next relative humidity step. You don't have to specify the exact same time for each humidity step. Now, I will be showing some data which also shows scannings of relative humidity, but most RH experiments are done this way. And from this type of data, you can construct something known as a sorption isotherm. This is where you take the very last data point in a relative humidity step, and now you plot that data versus the relative humidity steps that you've done. So that type of plot is shown in the lower left corner. From this type of graph, there are a number of things that you can do to analyze and things that you can learn from it. One is to maybe compare the hygroscopicity between different samples, so the ability of materials to take up water. Both instruments allow for this type of comparison. Another thing is to analyze the sorption isotherm shape. This is more prevalent in the Discovery SA, as we'll see. You can calculate the coefficient of hygroscopic expansion. Obviously, that is something that's going to be related to the TMA. And then you can look at both sorption and desorption curves here understand things, whether there's hysteresis in the curve. Does the sample release water as easily as it takes up water? And again, both instruments. This is something that's important to see in both instruments. So we'll jump right into an application here. This one's going to be, some of the applications here are going to be focused on electronics, so hygroscopicity, processing conditions, and material compatibility. So the first piece of data here is from the Discovery SA. So you can see we're plotting weight change versus relative humidity. This is on a polyimide substance called Kapton, and we're doing the experiment at 25 degrees Celsius, and we're stepping humidity at 5% intervals. So this is the sorption isotherm, which is derived from the stepped humidity experiment. The blue curve, as the legend indicates, is the adsorption, so where we're stepping humidity up, and the green curve is the desorption, where we step humidity back down. And we can see that the curve here is actually fairly linear. The material gains just a little over 1% humidity, going up to 90% relative humidity. And there is a little bit of hysteresis related to this material. But once we get back down to 0% RH, we see that it actually goes back to its original length. So information like this is important on a number of levels. In particular, this type of polyimide, Kapton, is used in flexible electronic PCBs. And it turns out that in order to, during processing, creation of the flexible electronic circuits, you need to pre-bake the Kapton first to drive the water off of it. Since we know even though it's only mildly hygroscopic, you need to drive the water off before you begin to construct the PCB so that you can prevent delamination down the road. So it's what this type of data can tell you and have an impact on processing conditions. The second piece of data here is coming from the Discovery TMA RH. So we're plotting now dimension change versus relative humidity. This is just a absorption curve, and we can see that we're taking steps of 10% relative humidity all the way up to 90% RH, and that's the blue curve, and that's related to the left-hand axis, which is the dimension change. On the right-hand side, we're plotting now the CHE, so the coefficient of hygroscopic expansion. And you can see that we're making this measurement between successive points on the curve. And the units here, coefficient of thermal expansion, if you're familiar with that, you know it's micrometers per meter per degree C is one set of units that you can use. In this case, very similar, it's micrometers per meter per percent RH. And just to give this some context here, so we see that this is, you know, roughly 15 to 22 micrometers per meter per percent RH. Anybody familiar with running TMA on aluminum will know that's a calibration standard that we provide. The CTE of aluminum, its thermal expansion is right around 20 or 22 micrometers per meter per degree C. So as far as expansion of this Kapton is on its CHE, its dimension changes roughly the same as you step RH. So this type of information is of course very valuable to know if you're going to make some type of layered material, which is going to include Kapton in it. Just as you want to match CTEs, you will likely want to match CHEs too. And as a final example here, this is now, we're looking at a material called perfluorosulfonic acid, or PFSA. This is a film material which is used in proton membrane batteries. It's actually a membrane that fits into them. It must function, those types of batteries, the interiors are exposed to water vapor. They must function, the way that they function is with water vapor and water around them. And so this material, its properties are actually very good for that function. But you can see we've actually plotted the Kapton data on the same graph here. and I want to say that this data actually is courtesy of Matt Lewis from our engineering department, you can see that PFSA has a very large expansion. It's more than an order of magnitude, its dimension change as compared to Kapton. So this again becomes something that is necessary for people to know when they actually are doing battery construction, so that you can avoid failures, increase the lifetime of the battery, take into account this very large increase in its dimension. And just as a comparison, you can see in the on the left-hand side, we have a comparison of the CHE versus the CTE of the PFSA membrane. So at 30 degrees Celsius, this membrane changes about 90 micrometers per meter per degree Celsius. But at 30% RH, you're looking at about 700 micrometers per meter per percent RH. So it's approaching an order of magnitude. Its CHE is about an order of magnitude greater than its CTE. So again, CTE is an important property. We know it's an important property to measure. Obviously, CHE is an important thing to know about this material as well. So let's take a little bit of a closer look now at these two instruments. So this is a cutaway view of the Discovery SA. You can see the balance at the very top there. This is a symmetric design. So the sample side and the reference side are exposed to the same temperature and relative humidity conditions. This is so that we can since water again will attach itself to any surfaces, we want to be able to know when water is actually attaching itself to the surface or going into the interior of the sample itself and not being attached to the pan. So that's why the reference side is now exposed to the same humidity and temperature as the sample side. And at the bottom there, you can see that's where the sample and reference chambers are, and the humidity chamber is actually integrated into this whole setup here. So this is a very compact system. So I spoke earlier of being able to control from 0 to 98% RH and 5 to 85 degrees Celsius. Our accuracy here is about plus or minus 1% RH. And the graph shown here is looking at some deliquescent salts. So lithium chloride, sodium bromide, potassium nitride, and looking at their measured deliquescence points relative to their true values, just to emphasize that we are meeting the plus or minus 1% RH here. Now, since these experiments are very, very long, of course you want to have very stable, in this case, weight signals so that you can be very sensitive to changes in weight that occur. You don't want the balance drifting either over that time period. So here we have a plot of the weight signal taken over 24 hours at 25 degrees Celsius and 20% relative humidity. And you can see that it's less than a half a microgram, probably around a quarter of a microgram here. And the chart at the bottom indicates our baseline stability under several different conditions. So the isothermal condition, plus or minus a quarter of a microgram. If you're doing humidity ramping, plus or minus a microgram. And if you're doing temperature ramping, again, plus or minus a microgram. So the stability for the true mass balance is excellent and is something that's critical for these types of experiments. Looking at the 450 RH, so again, this is a dedicated instrument. This is not an accessory with this. This instrument has been built and dedicated to looking at relative humidity. So the humidified gas comes from the accessory through the rear of the chamber. You can see a cutaway view now looking at the interior of the, you can see the quartz rod there down on top of the sample, which is held onto the quartz stage. Temperature and RH sensor mounted very close to it. The chamber's temperature is controlled by Peltier elements. That's the same as it is actually in the Discovery meant to mention that in the previous slide. So we use Peltier elements for temperature control. And I had mentioned in a previous slide that the RH versus temperature, it's not a rectangle like it would be on the Discovery SA. You can see a plot of what the relative humidity versus temperature looks like here. So up to about 90% relative humidity, it's roughly rectangle in shape, but then it, as you go up to the higher temperatures, it does begin to drop off, which is something that is typical. This particular relative humidity chart here is very similar to what you would see for our DMA and for our rotational barometers, which use the same humidity accessory here. So this is the control chart for this. And again, among our competitors, this is the best RH and temperature control range of any other instrument on the market. And just as with the Discovery SA, because there's long experiments here, we want to see very good, very flat baselines relative to dimension change. So here is a dimension change plot. Again, it's done for 24 hours. Same parameters, 25 degrees Celsius, 20% relative humidity. You can see we're probably less than 1/10 of a micrometer here. The specification is 6/10 of a micrometer. Again, if you want to do RH ramping, that's 6/10 of a micrometer, or temperature ramping, it's less than a micrometer. And the cutaway here shows the interior of the system. So the force transducer and the displacement transducer here are the same high quality components that we use in our Discovery TMA 450. So moving on to another set of applications here. So now we're going to be focused more on the pharmaceutical industry. So we'll be talking about active pharmaceutical ingredients like APIs, excipients, and delivery systems. So we have here a plot, a sorption-desorption curve on ibuprofen, which is an active pharmaceutical ingredient. We're doing this at 25 degrees Celsius. And again, we're stepping the humidity in 5% steps from 0% up to 90%. And this data is courtesy of Hang Lao, who is in our applications group. You can see here that as opposed to what we saw previously with the Kapton, this is really not linear in shape. This has more of an S-shaped curve to it, which is important to note. There is some hysteresis also on the downward part here, but once you get back down to 0% RH, the RH does, the sample weight does come back to what its original weight was. And so this type of data, again, the shape can become important to learn specific things. And the European Pharmacopoeia actually has different classes of material. They classify them as non-hygroscopic, slightly hygroscopic, moderately hygroscopic, or very hygroscopic, based upon what their weight uptake is at 25C and 80% RH. So in this case, we've outlined that with the red arrows. The weight uptake here is about 5.5%, which would qualify this sample as being moderately hygroscopic. That again then becomes important to know in terms of the uses that you want to have this drug be used for. Processing of this drug, how do you need to control RH in the processing facility and in the packaging of this drug? How are you going to package it so that it maybe is shielded from different levels of RH prior to its use? Now here is a scan of relative humidity. So we're not stepping relative humidity here, we're actually scanning it. And this is looking at an excipient. This is amorphous lactose. Lactose is a very popular excipient. It's excipient, something that's used to hold your active pharmaceutical ingredients so that you can make a tablet out of it. So we see here we're scanning the humidity up to just above 80% relative humidity. And again, this is Discovery SA data here. So we see that this material, looking at what's going on here, just prior to 40% relative humidity, there is a change in the ability of the material to take up moisture. It actually increases. So what this means is we've gone through the glass transition of the material. So in amorphous lactose here, water is going to be acting like a plasticizer. What a plasticizer will do is the more plasticizer that's incorporated into a material, the further the glass transition temperature is lowered. So at this point, when we reach about 40% relative humidity, so much water has been incorporated into the lactose that its glass transition has dropped below the isothermal temperature of the experiment, which is at 25 degrees Celsius. That's why it begins to take up water more rapidly. Just below 60% RH, all of a sudden there is a sudden drop in weight. This is due to crystallization of the material. And as it crystallizes, it forces water out of the crystal structure. This type of thing is very important to know. Lots of amorphous materials are unstable with respect to recrystallization. So an important thing to know about your materials. Here we're looking at another API, and we're looking at the formation of hydrates. So within active pharmaceutical ingredients, about 1/3 of all APIs form hydrates, meaning the water is incorporated in some stoichiometric fashion into the crystal structure of the material. This type of thing is very important to know because it can affect the dissolution, the bioavailability, and as we saw previously with lactose, if the water is forced out of the crystal structure, it actually may induce a crystal to amorphous change. So in this case here, in the middle graph at the bottom, we show again stepped humidity experiment up to about 90% RH. There is adsorption, desorption. There's 2 of those, and we find out that this material has 3 different hydrate formations. So it starts out anhydrous. It forms a dihydrate right around 55% relative humidity. And then finally it forms a tetrahydrate, so 4 water molecules per crystal structure as you get up to about 80% RH. There's significant hysteresis as you begin to bring the material back down. And you don't actually get back to the anhydrous form unless you go again all the way back to 0% relative humidity. If you stop earlier than that, you can take it into the monohydrate form. So this type of analysis is critical, and it's very common to do in the pharmaceutical industry. On the far right-hand side, we have a temperature scan now of this material, just showing a temperature scan. This is actually a temperature scan from high temperature to low temperature, showing the weight change as we go from the monohydrate to the dihydrate form at 65% RH. Moving now on to data from the Discovery TMA. Now we're looking more at drug delivery systems. So now we're looking at a gelatin capsule, and we're looking at again, this is a relative humidity ramp, so we're using this to compare a capsule at 2 different isothermal temperatures. And this data may look familiar to people that run TMA. This looks exactly like a glass transition detection would look if temperature were the x-axis. In this case, relative humidity is the x-axis, but it's the same thing. You are detecting a glass transition here. And so what we see is that for the gelatin capsule at 50 degrees Celsius, its glass transition occurs at a lower RH than it does at 37 degrees RH, at 37 degrees Celsius. And this is for the same reasons that we saw relative to the amorphous lactose. Water's acting like a plasticizer. It's lowering the glass transition temperature. And it just so happens that it lowers the glass transition temperature below the experimental temperature at a lower RH, the higher the temperature you're at. This is right in line with what we saw with the amorphous lactose. And now this is a dynamic scan on the same material. So we're looking at the gelatin capsule, but now we're modulating the force. And so now we're able to plot storage modulus, which is related to the elasticity of the material on the left-hand axis, and the loss modulus, which is related to the viscous response of the material on the right-hand axis. And we are using the peak in the loss modulus in this case as our detection of the glass transition. So this type of experiment, as you go through various thermal equipment from DSC to TMA to DMA, the ability to detect glass transitions increases. So DMA, or dynamic force types of experiments, are very sensitive to detecting glass transitions. So you have the ability to do that with the Discovery TMA RH. And you can see here, we see exactly the same thing that we saw in the previous one, except now we're looking at a peak in a graph. So it's easier to actually locate more consistently the glass transition as well in this type of experiment here. So knowing where the glass transition is, understanding that it can change depending on the humidity that it's exposed to, again, may be important in knowing how are you going to package and transport these types of materials. Talk about software for a moment. So we've already talked about how flexible we are in terms of setting up experiments. You can see at the top we have the classic type of experiment in the upper right-hand corner, which is stepped RH. We also have shown some ramped RH experiments here. So fast equilibrating samples or comparison between materials, measuring deliquescent points. Those are things where you might ramp RH. The lower half, we're talking about now stepping temperature or ramping temperature. So again, for fast equilibrating systems, maybe you're going to do temperature ramps at an isohum type of experiment. We saw that with respect to the sodium naproxen. And then you can step temperature just as you can step RH and perform, again, construct a sorption isotherm from that. So very flexible method control. And as far as the Discovery SA is concerned, I had mentioned in an earlier slide that the shape of the sorption isotherm is very important, especially with sorption weight curves. And that's because you can fit those types of curves to models and you can understand certain things from them. So if water is being absorbed just on the surface, you can potentially understand what the monolayer capacity is in terms of weight for particular substances. With porous materials, doing this type of curve fitting can tell you something about specific surface area. And you can compare then specific surface areas among different materials. So there's 5 particular things that we can analyze the data here. With the Henry isotherm, which is more of a linear type of fit. Langmuir, which is very popular to use among porous materials. BET and GAB, which are very popular in the food and pharmaceutical industries. And then we just have a free parameter model called the DLP model to use here. So the ability to take SA data and fit it to various types of curves is available within our TRIOS package. So we've talked about sorption isotherm generation model fitting, calculation of CHE, the fact that with the Guardian add-on, both of these instruments are 21 CFR 11 compliant. Control these instruments with a single PC, and since all of these instruments now, all of our other instruments are TMAs, DMAs, TGA, DSD, and SDT are all on TRIOS. You can control them with one PC, and you can bring in and overlay data, analyze them all within one software package. So some further applications here. I'll finish up with some further applications. So now we're looking at a Discovery TMA RH piece of data here. So this is now looking at an isostrain experiment. So in an isostrain experiment, we're going to apply a strain, change the dimension of the sample to a specific level, and we're going to hold that strain, or attempt to hold that strain, constant while we change something else. So in this case here, we can see that humidity, which is the blue curve, at about 400 minutes, the humidity dropped from 50% relative humidity down to 0% relative humidity. The red curve is the strain. We're holding the strain at 0.2%. And the green curve now is the force. And you can see how the force is increasing as we attempt to hold the strain constant under 0% relative humidity conditions. So this is now, the material had absorbed some water under 50% relative humidity condition. At 0% relative humidity, it begins to release that water and it wants to shrink. And so we want to measure the force that's necessary to hold this material in place as it begins to release water. This is very interesting to know in terms of, if there's going to be failure, if a material can absorb and then desorb that moisture, is there the potential for the material to fail due to shrink force? Are you going to get cracks in something? So your gelatin capsules or something like that. Is this going to lead to delamination of multi-layer materials here? So measuring shrink force, being able to track shrink force is an important application. Looking at the Discovery SA, now we're looking at packaging films that could be used in the food industry. So, of course, a lot of foods are protected from being exposed to moisture by packaging them with the appropriate types of polymer films which don't allow water into the system. And here we're just doing a comparison of two different films. You can see that the moisture uptake for either of these films is very low, only 0.3% when you're at 70% RH and 30 degrees Celsius. And you can see that there is different behavior between these films. And so being able to make these types of comparison can allow you to select what's the best type of film that you might want to use in this type of application. So here we have an experiment now done temperature ramping with the TMA RH. This kind of rounds out the different types of experiments that you can do. And this data is courtesy of Andrew Janis, who is in our applications lab. And we're looking at nylon here. So nylon is a polymer substance. It is well known that water acts as a strong plasticizer in nylon. It will lower its glass transition significantly if you load it up with lots of water. And in this particular data set, we're tracking this. So these are now isohume experiments done with temperature ramp. So on the blue curve, this is now done 0% RH, and we ramp the temperature under dynamic conditions again. So we're modulating the force. And now we're looking at the tan delta versus temperature. And the tan delta is the ratio of the loss modulus to the storage modulus. The previous data that I showed you, I was plotting storage modulus on one axis and loss modulus on the other. Here we're taking the ratio of those two components. And you can see that the glass transition is up around 80 degrees Celsius. We've now done isohume experiments at 15, 30, 45, and 60% RH. And when we get to 60% RH, we can see the glass transition has been lowered by almost 50 degrees Celsius here. The glass transition temperature is around 30 degrees Celsius. So again, this illustrates the detection capabilities of this instrument in terms of detecting glass transition under modulated force conditions, and the tracking of a very typical type of sample, polymer sample. And finally here, I'm just showing some data with the Discovery assay on some porous materials. Now, a lot of porous materials are used in gas separation types of applications. So you take dry gases and you want to separate them from, if you have a mixture of those gases, you want to separate a particular gas out of the gas stream. So, for instance, carbon dioxide within coal burning power plants. It's a very active area to try to separate carbon dioxide out of gas streams in coal-fired power plants. So you're using, in some applications or some methods, you're using porous materials that are sensitive to carbon dioxide. They want to uptake carbon dioxide, but nothing else in the gas stream. And then once you've loaded the material, you can remove it and desorb it and store the carbon dioxide or whatever gas you're taking out here into some type of container, such as a cylinder, which maybe they can be used for other applications. So uptake of gases, very popular application with porous materials. And you really want to know how sensitive are these materials, not only to other gases in the gas stream, because you want to selectively uptake only a certain gas, but also to moisture. So here we have an activated carbon sample and a zeolite sample. The difference here being that activated carbon is a nonpolar type of porous material, whereas a zeolite is more of a polar type of material. On the zeolite at the bottom, you can see that it almost immediately will take up water into its pore structure, and then it changes very little after that. So if there's any moisture around, a zeolite is going to take it up, and it's going to block the pore structure, and you're not going to be able to remove gases from the stream. Not the same with the activated carbon, where we see that it has some moisture uptake, but not like it is on the zeolite. And we can see that this is actually also a sorption-desorption. So again, there is some hysteresis that is seen there. Also important to know. So that actually brings me to the end of my talk. And Jason, I'll be happy to answer any questions.
Sure. Thanks, Gray. That was a great talk. There are a couple of questions that have come in. There is still some time to submit questions into the Q&A area that we can address before we log off here. But I'll start you off with I'll assume an easy one. Could you discuss some of the calibrations that are involved with each of the instruments?
Sure. So with the Discovery assay, so the temperature and the relative humidity signals are calibrated in-house. And when a customer obtains the instrument, they would be calibrating particularly the weight signal on that instrument. And then you would have a service engineer come in on a yearly basis to, again, verify the temperature and relative humidity signals for that instrument. On the TMA RH, again, the temperature and RH signals are calibrated in-house. But now when you get the instrument, you would actually be calibrating. Anybody familiar with a TMA knows that you will calibrate the force, application of force on that instrument. There is what's called a probe calibration on the instrument, which is used to measure a number of things on the probe, including its weight and its flexibility. And then you would also calibrate a cell constant for that instrument too, which is useful in terms of making sure that CTE values that you measure on that instrument are calibrated with respect to, say, an aluminum slug.
All right, thanks, Gray.
Sure.
So we have a couple of questions. I believe that they're kind of interrelated. But is there any specific way or methodology that you would want to, or that you can detect or just changes of materials in all three dimensions? How would you go about making those types of measurements?
So you would probably have to rotate, you would probably have to make measurements of the material, separate experiments of the material under different orientations. In standard TMA, there is a volumetric probe which allows you to put a sample inside of a container and you surround it with some silica, basically sand, and you lower a probe on top of that. And by measuring its changes in one direction, there is a mathematical formula that you can use to change that to volumetric changes in a material. We don't use the volumetric probe on the TMA-RH for the very fact that you have to bury the sample inside of a quartz vial with sand on top of it. So you would never have water, unfortunately, making its way down to where the sample is. So in order to understand changes in three dimensions there, you would set up experiments where you would then, separate experiments where you would probe the sample in different orientations. So for example, for an electronic circuit, to do an experiment where you have the layers parallel to your sample structure, sample holder, and then you may cut a piece where you orient it now where the layers are perpendicular to the sample pedestal.
Right. Thanks, Gray. The questions are flying in now. So
okay.
Sure. So here's a question about sort of detecting equilibration ranges. So is there something in the software or something in the instrument that on the TMA that allows you to determine when a material has reached equilibrium? Can you do that in a ramp environment? Does it have to be in a stepped environment? Because the experiments can be long and.
Sure. Yeah. So yeah, you would want to do that in a stepped environment. If you're ramping either temperature or relative humidity, you basically have told the instrument, I want you to change these parameters at this specific rate. So, but in the case of stepping experiments, so stepping relative humidity, which is the most popular, and this applies to both instruments here, you can tell it, step the humidity to a particular level of relative humidity, hold it there a maximum amount of time. So typically 1 or 2 hours maybe is what, depending upon how rapidly you think the material will absorb water. But you can also then say if the change in weight or if the change in dimension drops below a certain value, then move on to the next step. So for instance, in the Discovery assay, say step the humidity in steps of 10%, hold for 2 hours unless the change of weight is less than, say, a tenth of a microgram over a 10-minute span. And if that's true, then please move on to the next relative humidity step. And the syntax for that type of method segment is exactly the same as in the TMA-RH, except you're talking about, dimension change and detecting a minimum dimension change over some time period before moving on to the next humidity step. So yeah, those types of method segments are absolutely available.
Right. So sticking with the TMA-RH, can you expand on the types of probes and potentially the other types of materials or material forms that you might be able to also test with the TMA-RH?
Sure. So of course the probe that we feel is probably going to be the most popular is going to be the film fiber probe. So accessing films, looking at films and fibers, and it makes sense that in this case that would be kind of the most popular probe because you're going to have much faster absorption of water through thin films or fibers. But other types of probes that we offer, they're, as mentioned previously, except for the volumetric probe, they're exactly the same as with the TMA. So there's an expansion probe, which has a particular surface area that it sits on top of a sample. There's a macro expansion probe, which has a larger contact area that it applies to a sample. There's a penetration probe, which has a smaller contact area. Typically in the TMA expansion probe and the macro expansion probe are used typically to measure CTE, whereas the penetration probe can be used to measure glass transition. I don't see that those would be that different in the TMA RH. Again, so you may be using a penetration probe to look at and track glass transition changes in a material as a function of RH. There is the knife edge probe, which is can be used. So it's a 3-point bend probe. Sorry, it's a 3-point bend probe. So you have a sample which maybe looks like a cylinder or a plane surface, rectangular type of sample that's supported on two ends, and then a knife edge probe is brought and rests in the middle of that. So there's 3 points, 2 points of support, 1 point of contact. That probe will be used to calibrate the system for dynamic experiments, and that allows me to correct something earlier, that that's an additional calibration that would be done on the TMA RH, is to use that probe to calibrate for dynamic experiments. But you can also use it again to make measurements of samples in that type of configuration. Now, with all of these other probes, with the expansion probes and the penetration probes, if you're going to be using more solid type samples, so you'll want to have samples that are either cylindrical or square, that have planar surfaces on them, you will have to allow for longer periods of time for those samples to equilibrate at different RH steps. It can be done, but you just need to take that into account.
All right. Thanks, Gray. We'll finish up the session with one quick, easy one for you.
Okay.
And then before everyone leaves, I just want to make sure that you all know that these webinars will be archived and available later for replay. So make sure to check our website. But last question I have for you, Gray, is does the Discovery SA still have a pan punch option?
Absolutely. So you need to use the 25 position tray for this. So the 10 position tray is what's the standard tray on the instrument, but there's an option to get a 25 position tray. And so you're using, in this case, it's aluminum pans, and the punch opens, it's almost like a soda can. You will punch and push down on the top of the pan lid and push a section of the pan lid into the interior of the pan itself. This way, we know that there are a lot of other punches that use, say, needles or something like that. The way that we've designed the punch, which is the same for our other TGAs as well, is to prevent as much as possible contamination of the punch fixture. So by having the punch contact the lid and push the lid in, it should be contacting only the lid, should not come in contact with the sample, so that you don't get cross-contamination as you go to the second lid that you want to punch open. So those pans, again, you punch them just prior to loading into the system.
Thank you, Gray. And sure. With that, we are going to close out our Q&A session. Any questions that we have in the chat here, we will make sure to get back to you and answer you as soon as we can. I certainly want to thank all of you for attending our webinar. We certainly have a selection of other resources that are applications notes, brochures that are available for both the TMA RH and the Discovery SA. So make sure to check those things out on our website. And mention again, this webinar will be archived, so you can come back and catch some things that maybe you missed during the first session. So thank you again. We look forward to for you joining us again here in the future.
Thank you.